Okay, guys, welcome. In this video, we're going to talk about relations, right, and how they relate to bijective proofs. Now, a relation is a set of ordered pairs. By a relation on A, we mean a subset of A cross A, right? So a relation is kind of like a function, only we don't have the restrictions on not repeating a first coordinate, right? So a relation is simply just a set of ordered pairs. Now, many times we'll look at a certain type of relation, and that's what's called an equivalence relation, right? And that's basically just says that you have a relation on A such that for any element of A is equivalent to A, which means that the equivalence relation is reflexive. If A is equivalent to B, then B is equivalent to A. That means that it's symmetric. And if A is equivalent to B and B is equivalent to C, then A is equivalent to C. That means that it's transitive. Now, an example of an equivalence relation is just the simple equals. All right, I tried to sort of write that out, but it didn't really come out clear. Now, I have in the notes that another example is less than or equal to, but this is not right. This is false. All right. And of course, the reason why is this is not symmetric. Right? Because, for example, if 3 is less than or equal to 4, it does not imply that 4 is less than or equal to 3. Right? So this is not true. All right, so make sure that you sort of see that out there. Now, another thing that we have is that if we have an equivalence relation on a set A, and A is an element of A, then we define the equivalence class of A, right? So we sort of put it in these brackets here, and it's all the elements B such that B is equivalent to A, right? Now, we say that A is equivalent to B, and that's true if and only if they are the same, they give the same equivalence class. And if two elements are not equivalent, then their equivalence classes have nothing in common, right? So the intersection of their equivalence classes is the empty set. Okay. Now, one final definition here in regards to relations is that we say that a partition of a set A is a collection of non-empty subsets of A, which we'll call P, such that for any X that's in your collection of subsets A, there exists some U in your partition such that X is in U. And this is usually said to be that P covers A, which basically means that you don't leave anything out, right? So if there's an element in your set that you started with, then in your partition, you can find that element somewhere, right? And another thing says that if U and V are sets in our partition, subsets in our partition, then either they're the same or their intersection is the empty set, right? So another way to think of that is that they're disjoint or that there's no overlap. All right, so those are some sort of some definitions that relate to relations here. Okay, now we're going to talk about bijections a little bit more. Now we talked about bijections a little bit in a previous video, but I want to come back and I want to do that a little bit more. Now, remember that a function that goes from A to B that is both one-to-one and onto is called a bijection, right? So we say that A and B have the same cardinality if there is a bijection from A to B, right? And in this case, we'll say that A, and we'll use that equivalent sign to B, and or most of the time, I'll actually use this definition. We'll say that they're sort of their absolute value, which is really just means the size of the set is the same. Right? So most of the time we do this as follows. We show that it's one-to-one by showing that if f of A is equal to f of B, then that implies that A equals B. And we show that it's onto by showing that if f of x is equal to some C, for some C in your codomain, which we'll say is just B for now, then you can solve this for any C that's in B. Okay. So for example, let's show that f of x equals 2x minus 3 is a bijection, and we'll assume that this is going from R to R. Okay, so if we want to show one-to-one, again, what we do is we assume that f of x1, and I'll use a and b here since that's what I said. Assume that f of a is equal to f of b. And we want to show that a equals b. So then we get that 2a minus 3 is equal to 2a plus 3. Sorry, 2b minus 3. So then if we add 3 to both sides, we get 2a is equal to 2b, which we can then say that a is equal to b. So it's 1-to-1. Now for onto, we're going to assume that f of x is equal to c. Right? So if f of x is equal to c, then we get 2x minus 3 is equal to c. Now if I solve this for x, I'm going to get that 2x is equal to c plus 3, and then so x is equal to c plus 3 over 2. And since this is from the reals to the reals, x can be any real number, c can be any real number, so I have a formula that will get me any number that I want in the set of reals. So this, of course, is onto. So this is a bijection, since it's both 1-to-1 and onto. Okay. So now, as an example, we'll prove that for any sets A, B, and C, that A is always has the same cardinality as A. If A has the same cardinality as B, that implies that B has the same cardinality as A. And then the transitive property A equivalent to B, B equivalent to C implies that A equivalent to C. Right? So let's show that for any sets that this will work. So first let's show A is equivalent to A. Right? Now for this, an appropriate bijection would just be the identity map. Right? So this is a 1-to-1 onto mapping from A to A. So then A is equivalent to A. Now, if we have that A is equivalent to B, we want to use that to show that B is equivalent to A. And of course, the idea is that here our bijection would just be the inverse, right? So if the bijection from A to B is f of x is equal to y, then for B equivalent to A, we would use that x is equal to f inverse of y, right? Because once A is equivalent to B, that means that this bijection exists. So to go backwards, we would use the inverse. Right? Now for part 3, we have the A equivalent to B and B equivalent to C. Right? So now what would work here? Well, let's say that F goes from A to B is our bijection from A to B, and let's say that G is our bijection from B to C. Well, then that all that means is that G circle F is a bijection from A to C. Right? So then that shows that we have a 1-to-1 mapping or a bijection, 1-to-1 or an onto mapping or a bijection from A to C. Right? So A is equivalent to C. All right, so that's how we can show these set equivalences using appropriate bijections. Okay, now what we're going to do is we're going to state and prove the theorem that for any open interval on the real number line, that open interval has the same cardinality as 0 to 1. Right? Now for the proof, the hint is to show that A and B, that A comma B is equivalent to 0, B minus A, and then that 0 comma B minus A is equivalent, to 0 comma 1 with appropriate bijections. Okay. Now first to show A comma B is equivalent to 0 comma b minus a, then what we need to do is just need to take f, whoops, yeah, x is fine. F of x is equal to x minus a, right? So then that would take a to 0, because if you plug in a, you get a minus a, which is 0. If you plug in b, you're going to get b minus a, right, which is what we want. All right, and of course this is 1-to-1 and on to. Now we want to show that 0 comma b minus a is equivalent to 0 comma 1. And of course the way that we do that is we want to bring f of x equaling x over b minus a. And of course when we plug in 0, we're going to get 0 back. When we plug in b minus a, we would get b minus a over b minus a, so that would give us 1. And of course this is also 1-to-1 and on to. All right. So now finally, we actually did these in a previous example, but I just want to sort of refresh your memory on this. So we have that the integers are equivalent to the natural numbers, right? And again, we did this before by saying that the natural number is 1, 2, 3, 4, 5, 6, 7, 8. Can line up with the integers in this way, right? So we have 0, 1, -1, 2, -2, 3, -3, and so on and so forth. And of course, it turned out that the bijection that we used was f of x being a piecewise function. It was x over 2 for x being even, and it was 1 minus x over 2 for x odd, right? And that would give us, this one gives us all the positive integers. And this would give us all the negative integers and zeros. All right, and then of course you can show the same thing for the rational numbers being equivalent to the natural numbers. And I realized before I was writing this up that we did this already, so you can look at the previous video for this as well. All right, but that, a couple more definitions. So a set A we consider to be denumerable if there's a bijection from the natural numbers to A, right? So in other words, it has the same cardinality as the natural numbers. Now, if it's denumerable or finite, we say that it's countable, right? So another way you could say that it's denumerable is that it's infinite, but it's countable, right? And of course, if it's finite, it's also countable. Otherwise, we say that A is uncountable. Now, are the natural numbers union with the negative natural numbers countable? Of course, the answer here is yes, because this would give you the set 1, -1, 2, -2, 3, -3, so on and so forth, right? And this is a subset of the integers, right? Because the integers also include 0, and this is countable because we could form a 1-to-1 and onto function from the natural numbers to the integers, so that's countable, so this is also countable. Right? So it looks like the union of two countable sets is also countable. All right, and finally, the last thing that we'll say is that a countable union of countable sets is also countable. So you can actually take something like the natural numbers, let's put it this way, union 1/2 times the natural numbers, union 1/3 times the natural numbers, union so on and so forth. That would also even be countable. And this is something that we'll prove later. But that concludes this video on relations and bijections. I hope you enjoyed, and I'll see you next time.